Hello and welcome to the presentation Average Density Detectability in Traffic Networks using Virtual Road Divisions. In this presentation, we consider traffic networks where sensors are located only at the boundaries, and we know that monitoring the entire state of the traffic network, so the density in each road, can be monetarily and computationally expensive. And therefore, we are only interested in knowing or reconstructing the average density of the entire system without needing to know the individual density of each road. So we start by defining what we mean by a traffic network, which is going to be represented by a weighted directed graph G, which will be composed of a set of nodes N, which represent the roads, a set of edges E, representing the turns or the connections between of the roads. We also have the adjacency matrix R, which corresponds to the turning ratio matrix. And also we have physical parameters, which are L, the length of each of the road, and V, the velocities of the roads. We are interested in following the dynamics of the state rho, which is the density of each road. And as we're only will be considering free flow dynamics, we can write it in this linear form, in which the transition matrix A will be written in this form, which depends on the velocity, the length, and the turning ratio matrix. And we have also this input term that just corresponds to the input demands and the location of the boundary inflows. We're going to do a partition of the state into two vectors, in which the first one, row 1, will correspond to the internal roads, and row 2 will correspond to the boundary roads. And accordingly, we're going to do the same partitioning corresponding to the matrix A and matrix B. And as I said before in the introduction, our state equation, Y, will correspond to the boundary nodes that we assume that we are able to measure. Therefore, using this information, we want to reconstruct the average density, which we'll define in this way, corresponding to the arithmetic means of the internal nodes. So we want to know the average of only the interior of the network. By plugging in this definition of the partitions into the dynamical system, we can obtain this equation for the trajectories of the average density, in which the important part is that we have this contribution of sigma, which is defined in this way: the difference between the real values and the average values of the densities of the internal nodes, which for us is unknown input signal. As the estimator, we'll be considering a simple open loop observer, in which the only difference is that we are omitting the effect of sigma, because as we said, it's an unknown sigma, an unknown signal. And we introduce the definition of average detectability, which states that a system is called average detectable if and only if this open loop observer converges, which means that the estimate of the average density, rho hat, goes to the real value as time goes to infinity. And in the literature, there is this result, this theorem, that states that a system is average detectable if and only if the column sums of the matrix A11 are all equal to constant negative gamma. We can see that this condition is very strict, so we ask the question. We know that traffic networks are not in general average detectable, but we want to ask, is it possible to find a new representation, a new graph, by splitting roads into smaller cells? To show this, to illustrate this possibility, we introduce the following motivating examples, in which the first is a simple linear road, in which we will be partitioning into three cells. The first choice is to have the cells of equal length, but if we calculate the transition matrix and do the column sums, we'll obtain these results. Note that do not satisfy the theorem, and therefore is not average detectable. Now we consider the same scenario, but we change the length of each cells, but these particular choices that are shown in the picture, And for this case, if we calculate the matrix, the transition matrix, and do the column sums of the matrix A11, we'll find that indeed, for this particular choice, we do satisfy the average detectability conditions. In the next example, we're considering a simple circle road in which we want to calculate how many partitions do we need for the top and bottom part, assuming that we have sensors in the green nodes, which are the incoming and the outgoing roads. We assume that the top part is divided into N1 cells and the bottom part into N2. And we are going to assume that the length of each road, of each cell, is denoted by delta. So we have a delta 1 for the first cell, delta 2 for the second cell, and so on and so on. If we calculate the transition matrix and do the column sums, we will obtain a system of equations of this type, one equation of this form, that we have the turning ratio, and many equations of this form. And if we put physical constraints that the sum of the cell lengths must be equal to the original length, we must solve this equation for N1 and N2. As we can see, the summands are a little bit different, that we have R here and not here, and therefore the solution must imply that each road must be divided into a different number of cells. So in a more general manner, our problem is that for any given network G, we want to find a virtual network G of n, where n is a vector of integers that specify how many, the number of partitions or divisions. For example, road I is going to be divided into ni cells. And we also must specify the length of the cells, here called delta, and the velocities of the cells. Using the notation here that delta ik is the length of the k cells of the road I, and same goes for the velocities. The divided graph we call the virtual graph, and we say that a virtual graph is admissible if the velocities of the cells are equal to the velocities of the original road, and if the sums of the cell lengths are equal to the original length. And then we define our problem as to be able to, for any given traffic network G, we want to find the number of partitions, the lengths of the cells, and the constant gamma, such that the graph G of n is admissible and average detectable. So we introduce now the results, and the first one we express in theorem 2. The proof is in the paper. We state that if we have the original graph G and an admissible graph G of n, then G of n is average detectable if and only if there exists the following relationship between the partition vector, gamma, and the vector of cell length. And it states that the cell of each length will depend in this way. We have these parameters Vi, and here this vector that will depend only on the turning ratios and the velocities. And we see the effect of the partition n and gamma. So we can use this theorem to solve the problem. And if we replace in the constraint that we want the total length of the road to be equal to the sum of the lengths of the cells, and then we use the theorem to replace the cell length by this expression, we obtain just a system of m equations in which the unknowns will be the n's here and here, and the gamma. However, solving these equations is a harder problem because not the unknowns are in the top of the summation. And to find solution, if there exist, they require expensive computations. Therefore, we need to find an efficient method not to solve this problem efficiently, but to solve it approximatively. Which means, in a more precise way, if we define this error function f, which is defined in the same way, we want to find a vector n and a scalar gamma such that the magnitude of the error function is small for all of the internal nodes. This leads us to our next result, which allows us to confine the approximate solutions. And the first theorem is that if instead of looking at integer solutions, we look at real solutions, and we have this matrix that depends only on the turning ratios, the velocities, and this matrix K that depends only on the gamma, the lengths and the velocities of the roads. And we say that if X solves this solution, this matrix, we know all of the parameters, and we let the n to be the nearest integer for each element X, then the error function will be of the order of this expression. And note that n is in that denominator because of the exponent. So if we have a lot of partitions, then the error will be small. And this goes well with this second theorem, theorem M4, that states that there exists a maximum gamma for which all of the values of gamma below of that maximum bound, the solution of this matrix is positive, so this X will be positive. And also, as gamma approaches gamma max, the maximum value, the magnitude of X will go arbitrarily big, and therefore we can make this magnitude arbitrarily small. To show in a more graphical way how to use these theorems, or which are the results, we take as a simulation example this network, which is a Manhattan grid of 4x4 intersections, in which just by simplicity we set all of the turning ratios to be 50%. The green nodes are the boundaries that we have sensors, and the white nodes are the internal nodes that we're interested in. So we want to know each of these nodes, how many partitions do we need. So by letting gamma, we are going to try different values of gamma from just 88% to 100% of the maximum bound. And we see here in this plot the solutions to this matrix here, this system of linear equations. So see that this matrix here depends on gamma. So by changing gamma, we're going to have different solutions. And the solutions here see that as gamma approaches the maximum value, we are going to obtain an increase in magnitude. But again, if we have a big magnitude of the partition vector, this means that the error functions will go to 0. By choosing just arbitrarily one value of gamma of 95% of the maximum value, which correspond to an error of about here, let's say 3%, we obtain this network. Let's see, here we have this road was partitioned into 2 cells, this one was partitioned into 3, and this one was partitioned into 4, so on and so on. And then we perform a simulation in which we assign some arbitrary input demands, and we plot the trajectory of the real average value in blue, and in red we have the estimated average value. And we see that originally there is a difference, but as times go on, they both coincide. So the estimator is in fact convergent using the equation that we established in the beginning. And we have to note that we, even if we obtain a different representation that has many cells that are very small, in fact, we do not need this virtual graph because for the estimator, the gain is, we can show that is just gamma. And also we have here the boundary nodes that we do not partition and that we measure directly. And this matrix over here will depend on the values of delta, but its dimension will be as the same dimension of y. So in fact, we do not need to know the entire graph, just the length, the number of partitions, and the size of this estimator is still small. and the calculations can be done offline. So in conclusion, first, we proposed a method that allows to construct a modified virtual network for which the open loop observer exists for the average density. The required calculations to obtain the physical parameters, which is the number of partitions per road and the cell length, can be done offline. Second conclusion is even if the proposed solutions imply the division of the original graph into a virtual representation with many cells per road, this graph is not actually required for the observer. We do not need to find the transition matrix. We do not need to find the entire representation. We just need to know the vector n and the vector delta. And finally, the goodness of the approximation is of the order that we find here, that will depend on n. And this says that the error will decrease with increasing n only if this delta is different from 0. It can be that it is equal to 0. However, if the graph is strongly connected, so which is typical for traffic networks, then we have the guarantee that d is different from 0. And then we have the guarantee that the error will decrease. For the future work, we would like to propose an algorithm how to improve the efficiency of the calculations of gamma. We want to expand the scope of the region of the dynamics to include congestion. And we want to analyze the difference of the dynamics of the original system and of the partition system. Thank you for your attention.